Alright, in this video I will be working the Unit 4/5 FRQ examples from the FRQ packet. So this first problem on the packet is number 4 from 2018. At this time, just go ahead and pause it, read the question. I'll mostly just focus on the solutions in this packet. Okay, so this is 4D from 2018. This is a related rates problem. So the way you identify a related rates problem is if you look on your study guide for the related rates box, I've given you this setup of find, when, and given. Okay, but how do you know that you're supposed to actually use related rates, or when do you identify that a problem is asking you a related rates topic? The way you can identify it is you can find this word right here, when. When something is at a fixed moment, it has a fixed measurement at a certain moment. So when. Okay, so this problem is talking about the tree and its diameter versus its the height of the tree. So the when in this problem is when the tree is 50 meters tall. And I'm going to use h equals 50 for the when. And then the given is usually some type of a rate in the problem. So if you use a different color, diameter of the base is increasing at a rate of 0.03 meters per year. So here we have a rate of the diameter. And so whenever we write our rate, it's going to be d something over dt, usually with respect to time. If you look at the units, it's with respect to time. And the diameter is measured using the variable x. It says x is the diameter of the base. So if you're using the rate of change of x, that's dx dt. So here we go, dx dt, the rate of change of the diameter. It said it was increasing at a rate of 0.03 meters per year. Okay, and then the find is usually in the question. So I need to go look at my question and figure out what am I trying to find. It says what is the rate of change of the height. Okay, now height is given by this function g here. So I need to figure out what's the rate of change of this. It's saying what is the rate of change of the height. G is representing the height. The rate of change of it would be g prime, or dg dt. dg dt equals, we don't know what that is. We need to figure out what that is. So we need to find, in a nutshell, what is dg dt when h is 50 meters, given that the rate of change of the diameter of the tree trunk is 0.03. So the way I need to set this up is I first need to look at my equation. My equation is g of x equals 100x over 1 plus x, and I'm trying to find its derivative, the first derivative, which is g prime, or dg dt. So when I take the derivative, notice how this is a function in terms of x, but I'm deriving with respect to t. So when I derive this, I'm using implicit differentiation because x is not the same as t, it's a different variable. So I'm deriving these terms with respect to t now. So I'm still going to use my same rules. This is going to be a quotient rule. Low d high, so 1 plus x d high minus high d low, 100x times the derivative of the denominator is just 1, all over low squared. But since I took the derivative with respect to x here, I need to multiply by dx dt. So now I have all the elements. My unknown is dg dt, and I need to plug in whatever I know over here into this equation here now. So I know dx dt is 0.03, so I'm going to put 0.03 back here. and I know that h is 50. Now h is the height and x is the diameter of the tree. So I can't just put in a 50 wherever I see x, because 50 is representing the height when x is going to be the diameter of the trunk. So I need to use this 50 to try to figure out what is the value of x when h is 50. So h is 50, which means that the height and g are the same thing. The height is modeled by this function g. So what I need to do is figure out if I have 50 is equal to 100x plus 1 over 1 plus x right here. I'm replacing g of x with 50 because I'm looking at the moment when the height is 50. What is the diameter? So if I solve this guy out, x should be equal to 1. So I'm going to put a little bit of a more indication here on the when part. H is 50 means that x is equal to 1. Okay, because if I plug in a 1 right here, 100 divided by 1 plus 1, 2 is equal to 50. So now that means I can plug in a 1 everywhere I see x here. So this will end up being 200 minus 100 divided by 1 plus 1, which is 2. So right now you have a numerical expression as your answer, and you could leave it like that because it's basically saying 200 minus 100 over 2 times 0.03. All the problems on the free response questions any year are made so that you can solve it without a calculator. You're not required to simplify a numerical expression here. So you can leave it like this just to be safe, or if you wanted to solve this out with your calculator, this entire thing will end up be equal to 3/4. The next problem is number 2 from the 2018 test. This one is talking about a particle that's moving. So if you have a moment, go ahead and pause it, read the question in full, and then we'll work the problem. Okay, so part A here is asking to find the acceleration of the particle. Now we know the acceleration is the derivative, so this is going to be pretty straightforward. We have the velocity function. We want to find the acceleration. So I'm going to put a of t, which is what I'm using for acceleration, is equal to the derivative of the velocity. Now, this problem was number 2 from a past year. That's a calculator question, so I don't really need to show my work to derive this, but it would be a quotient rule. But since you have your calculator, you can use the math 8 function, push the math button, and then number 8 allows you to take the derivative and plug in a point. So what you want to do here is find a of 3, which is equal to v prime of 3. So what you do is you do math 8, plug in this function here, and then where it says x equals, you would put the 3. You can use x instead of t in your calculator. So when you do that, you end up getting, for your answer, it's going to be a decimal. Let me pull it up real quick. The answer you end up getting here for the acceleration is negative 2.118 when you do that. Okay, so that's part A. Part B is asking to find the position. The position is, you can interpret the position in 2 ways. The first way you can interpret the position is you take the starting point and you figure out where you are based on that starting point. If you have your velocity though, you can integrate your velocity and it'll tell you how far you've moved. The area under the graph of the velocity tells you something about the position because the position is the antiderivative of velocity. So right here, the way I would set this up is with an integral by taking the integral of v of t dt. Now when I antiderive the velocity, I get the position. So this is equal to p of t plus c. Okay, but here I don't need this plus c because I know some specific bounds here. I'm trying to figure out what the position is at time 3. So I'm going to put a 3 up here for my top bound. I'm going to erase this antiderivative real quick here. And right here, if you look, the particle is at position x equals -5, or position units -5 when t equals 0. So I'm going to put the t equals 0 as my lower bound here. So now I have a definite integral. When I have a definite integral, I take the antiderivative. So we already said that's p, the position. But then I would evaluate my bounds, p of 3 minus p of 0, because 3 and 0 are my bounds here. P is the antiderivative. So I need to use this equation right here to figure out what's the position at time 3. We want to figure out what this guy is right here. Using your calculator, you can figure out what this guy is right here by doing math 9. Math 9, you integrate from 0 to 3, put in this function right here, and then that should give you the value for that. And we also know what p of 0 is. It's right here. It's this -5. So I'm going to rewrite this guy right here one more time. So 0 to 3 are my bounds. P of 3 is what we're trying to find. And this is minus p of 0, minus -5. P of 0 is -5. So minus a -5 is a +5 right here. So this tells me that p of 3, if I wanted to isolate it, I would just subtract over the 5. So I would have 0 to 3 v of t dt integrated. And since I'm subtracting over this 5, I would do a -5 there. Okay, so this guy right here, math 9 in your calculator, subtract 5 from that, and you should get the value for p of 3. This ends up being -1.760 in your calculator. Okay, so there's this problem right here. All right. Next problem is number 1 from the 2017 test. Just a little bit of background of this problem. This problem requires you to use the model from part C. So if you'd want to, or you like to, go ahead and find this online and do part C first. But just if you're working on this part D right here, part C, f of h was given as this function right here. And we'll need it in part D right here. So this is another related rates problem. So I'm going to go ahead and put my find when and given over here off to the side. So I need to go through this problem and find where those words are. So when is usually the easiest one to find because the word is when the height of the water is 5 feet. So I'm going to go ahead and put h is equal to 5 for my when. I'm going to look for my given, which is a rate somewhere else in the problem, usually somewhere close to the when. Okay, here's my given portion. It's giving me that the height is increasing at a rate. So the height would be dh dt. That rate is 0.26 feet per minute. So I'm going to put that down here. The given dh dt is 0.26 feet per minute. All right, and now we need to see what we're trying to find. We're trying to find the rate of change of the volume of the water. Okay, so that would be dV dt here. Okay, the rate of change of the volume, dV dt, that's the first derivative of the volume. Okay, so I need to set up this equation here. It is telling me to find dV dt. So looking at the volume equation here, just give me a second. Okay, so in this problem, it told me that the volume of the water, V of H, is equal to the integral from 0 to h of f of x dx. Okay, so this model right here was given from part C as well. I forgot to write that up here. This equation right here was given from part C. So what we need to now do is figure out what's dv dt based on this equation right here. This would be the setup. So taking the derivative of the volume with respect to t, what I need to do here is, so the dv dt portion right here is equal to, and so what I need to do with this side is take the derivative. If I take the derivative of an integral, and my top bound is in h, this is the second fundamental theorem of calculus, where we drop this variable into the function here. So the derivative here would end up being f of h. But since I'm taking the derivative with respect to t, I need to add a dh dt over here, because whenever I use the second fundamental theorem of calculus and I drop this bound into here, I need to multiply by the derivative of the bound. So that's why I did dh dt, because I dropped the h into the function, so dh dt henceforth. So I have this first derivative function here now, and now I need to take whatever I have over here and just plug it in. I want to find what dv dt is. So dv dt ends up being, so I'm just going to leave this as f of 5, because h is, when h is 5, here's h, 5, plug it in there. We know dh dt is 0.26, so times 0.26. Okay, so this f of 5 is referring to the function that was given in part C in this entire problem. Part C, here's f of h, so f of 5 would be a 5 plugged in wherever you see h, and then you'd multiply by 0.26. And when you do that, you end up getting 1.694419. Okay, and remember, it's preferable, I advise that you leave the entire decimal there. Don't try to round it or anything. That could put you at risk of losing points. Okay, so there's 2017 number 1. Okay, here's 2018 number 3. Okay, go ahead and take a moment to read it. Okay, so this problem is asking us to find the interval or intervals when f is both increasing and concave up at the same time. Okay, so looking at your chart, looking at your study guide in the box that has function analysis, I drew that chart there, talking about when a function is increasing and concave up. So if you look at that column of when f is both increasing and concave up, you'll see two things. So I'll write it up here just in general. F is increasing when f prime is positive. And then the second thing is f is, for this problem we're talking about concave up. I'll abbreviate there, but you shouldn't abbreviate on the test. Try to write it all out. F is concave up when f double prime is positive or f prime is increasing. Okay, so we have these two statements here that I'm going to base my answer off of. I know f is increasing when its derivative is positive, or f is concave up when its second derivative is positive, or if you don't know anything about the second derivative, or its derivative is increasing. In this problem, it tells us that g is the derivative of f. So g is also equal to f prime. So over here, all of these guys, not f double prime, just f prime, could be rewritten as a g. So I will indicate that in those statements. These are not my answers, I'm just writing that there so you have some context and some background of what I'm basing my answer on. So f prime is the same thing as g. Those two things are interchangeable in this problem because it tells that to us. G is the derivative of f. I need to find when f, the original, is both increasing and concave up. So I need to find both of these guys right here on the graph of g. One is g positive and one is g increasing. So if I take a look at that graph, g is positive and increasing right there because it's above the graph and going up. G is also positive and increasing on this parabola portion just on the right side from 4 to 6. So those two highlighted portions are when we have both f is increasing and concave up. So now I need to write this all out nicely and neatly in a couple of sentences or in a sentence. So when you write your sentences and your statements, when you give a reason for your answer or justification and for your response questions, you need to be really precise and thorough in your sentence so you don't leave anything out. That would be essential to giving you points. Okay, so here we need to focus on the interval from -5 to 6. So -5 to 6. Okay, so our first interval is from 0 to 1. The next one is from 4 to 6. So I'm going to start by saying what's going on. F is increasing and concave up on the intervals. I have two of them that I highlighted on the graph. On the intervals 0 to 1 and 4 to 6. 4 is less than x is less than 6. Okay, I'm writing what's going on. I've written the intervals that it's asking me for. On what open intervals? So I've answered that part, but I need to give a reason why. So here's the essential important part. That's right, because, and here's where these two sentences at the top come very handy, and this is also on your study guide. I need to write because f prime of x, or in this problem, the same thing as g of x, f prime of x is equal to g of x is positive and increasing on those intervals. Okay, there you go. So really specifically, increasing and concave up, and I wrote positive and increasing right here. Okay, this looks very similar to what you might have done in Delta Math in the past. Okay, these guys correspond with each other. F is increasing corresponds to F prime is positive. F is concave up corresponds to F prime is increasing. Okay, so notice the structure of my sentences here, that I've really organized this work and this sentence to show that I really know what I'm doing here. Okay. Next question. Okay, this is 2018 number 5. It says, let f be the function defined by e to the x times cosine of x. We need to find an absolute minimum value here. So whenever you see this word absolute, you want to check your endpoints. Okay, that's one thing that is essential when you're looking at the absolute minimum or maximum. What we're trying to do here is we're looking in between 0 and 2 pi on the graph of this guy right here and seeing what is the lowest most point, the absolute minimum here. Okay, so the reason we need to check our endpoints is because there may not be a minimum point in between 0 and 2 pi. It may just be going, in a linear path from 0 to 2 pi, and it will never look like it has a little, dip in it where there's a minimum point. So in that case, the absolute minimum would be one of your two endpoints. What we need to do is first figure out, are there any of those little dips inside of this interval in between 0 and 2 pi? So what we want to do here is we want to check our first derivative test. We want to figure out, when is f prime of x equal to 0? Okay, because whenever f prime of x equals to 0, that's our critical points. Okay, when are our critical points? So we need to first take the derivative of this guy. So it's going to be a product rule. So f prime of x, derivative of the first times the second, plus derivative of the second times the first. The derivative of the second is negative sign, so I'm going to put a negative e to the x sine of x. So we need to see when is this equal to 0. Factor out an e to the x, cosine of x minus sine of x equals 0. Okay, so e to the x does not ever equal 0, but cosine minus sine of x could equal to 0. It's when cosine is equal to sine. So this occurs at 2 points. This could occur at x equals pi over 4. That would be at your 45-degree mark on your unit circle when cosine and sine are equal, or in your third quadrant when you have 5 pi over 4. So here's two of your critical points. Now what we need to do is, so I'm going to draw an arrow, critical points. So we got those two critical points, and we got these two endpoints here. So what we need to now do is figure out which of these x values has the least or the lowest number, lowest y value. So if I plug in each of these into the original function, you can do that using your calculator. And what ends up happening, your lowest value ends up being, let me pull it up real quick. Your lowest value ends up being at 5 pi over 4. So I'm going to do f of 5 pi over 4 ends up being equal to negative 1 over root 2 e to the 5 pi over 4. All the other values end up becoming positive, so this is being negative would be the absolute minimum value. All right, there you go. Okay, number 2017, number 2. This problem is a traditional rate in, rate out problem where it gives you two rates. One rate is something being added to something, the rate at which something is being put into something. And then the other rate is something being taken out. And this is a very fundamental application of many things in the real world, of things changing. Okay, so this one is talking about pounds of bananas at a grocery store on a display table. So people are buying bananas, so that's the rate out, and then the grocery store restocking the bananas would be the rate in of putting more bananas on the display table. Okay, these are two different rates. They're not happening at the same rate. They're two different rates. People are taking them at some rate, and then the store is putting it back on. So part C of this problem asked, is the number of pounds of bananas on the display table increasing or decreasing at time t equals 5? So what that means is, with both of the rates combined, is the rate of the bananas increasing or decreasing, taking into account both of the rate in and the rate out? So what I'm going to do here is I'm going to kind of visualize this in a different way. So I'm going to put number of pounds right here. Okay, the number of pounds is a value. Okay, one level down, meaning its derivative, is the rate at which that thing is changing. So if I take the derivative of this guy, I'm going to put rate of number of pounds. All right, the rate of number of pounds of bananas. All right, so that would be like if the number of pounds was like, let's just name it a function. I'll just name it capital B of x, B of t. Okay, if you gave the number of pounds a function, the rate of change of that would be b prime. For example, like that. Okay, so this rate of change b prime would be equal to these two rates up here combined. Okay, what I'm trying to do here is I'm trying to incorporate the rate in and the rate out together. And so here, the rate in is what I would take into calculation first, so f of t, but then the rate out is what I'm subtracting. It's being taken out, so a negative or minus that. And the rate out was, sorry, I wrote this backwards. It should be g of t first because that's the rate in, minus the rate out, f of t. Okay, g of t minus f of t. So what I need to figure out is, the question is asking, is the number of pounds in the pounds of bananas on the display increasing or decreasing? So is this guy increasing or decreasing? So over up here in this top level, I need to figure out, is it increasing or is it decreasing? Well, the way we do that to figure out increasing or decreasing is we use that chart and we see when is the derivative positive or negative. So I need to figure out, is this guy positive or negative? That'll tell me if the number of pounds is increasing or decreasing. So if you were to figure this guy out using at time equals 5, at that moment, I'm plugging in a 5 into these guys. So what I want to do here is figure out what is g of 5 minus f of 5. And this is a calculator problem. You're not expected to plug in 5 and figure it out on your own in here. Use your calculator, plug in a 5 into here, plug in a 5 into here, and subtract them and see what you get. In this problem, when you do that, this is part C. So g of 5 minus f of 5, when you do that, you end up getting negative 2.263103. Okay, this value is less than 0, which means it's negative. Okay, that value is negative. G of 5 minus f of 5 is negative, which means that at t equals 5, the number of pounds is decreasing because its derivative is negative at that point. So right here, I need to write this all out nicely in a sentence. I'm going to say the number of pounds is decreasing. Okay, here's where you have to be careful. If it asks you for a particular point, you have to put that particular point at t equals 5. I'm going to say because g of 5 minus f of 5 is less than 0 or negative. You could put either way there. Okay, and that should be sufficient enough to answer the question here. Okay, let's go to the last page now. Okay, right here we have question number 3 from 2016. Question 3 from 2016, these are parts A and B. Okay, so we have this graph here, and we also have this. This is what's called an integrally defined function. It's a function that has an integral in it. All right, what we need to figure out first is, does g have a relative min, relative max, or neither at x equals 10? We need to justify our answer here. Okay, so in order to find a relative minimum or maximum, we need to take the first derivative of whatever we're finding it for, g. So for part A here, I'm going to find g prime of x. Since this is an integrally defined function, I need to use the second fundamental theorem of calculus where I drop x into the function here. So the derivative of an integral is f of x, just like that. So g prime is equal to f. And to find the critical points, I set that equal to 0. So right here, I need to figure out when f of x is equal to 0. Well, this problem is asking me in particular for x equals 10. So if I look at x equals 10, yes, it is a critical number because f is equal to 0, and f is the derivative of g. It's asking me, does g have a relative min, relative max, or neither here? So if I take a look right here, if you remember back to when we did the first derivative test, I would draw this number line here. Okay, the derivative goes here, f, and the original goes at the top. and I put my critical number on the number line. Okay. If I look at f, it's negative on either side here. Negative, negative, which means that g is decreasing, decreasing. So if I think about what's happening at the point x equals 10, my graph of g is going down, and it's leveling off here. Okay, it's going down, levels off, and then it goes down again. So this is neither. This is going to be a neither. So I'll say g is neither a relative min or relative max at x equals 10 because, and I'm going to say f, sorry, not f prime, f of x was equal to g prime of x does not change sign. Okay. We didn't have a sign change here, which means we can't have either a relative min or a relative max. If there was a sign change, then depending on what the sign change was, whether it's positive to negative or negative to positive, it would be relative min or relative max depending on that. Okay, so there's part A. Part B says, does the graph of g have a point of inflection at x equals 4? So when do we have a point of inflection? We have a point of inflection when the second derivative changes sign. Or in this case, when does f change from increasing to decreasing? So if I look at the point x equals 4, at x equals 4, the graph of f changes from increasing to decreasing. So I'm going to say yes, g has a point of inflection at x equals 4 because f prime of x, which is equal to g double prime of x, changes sign. Or you could also just put f changes from increasing to decreasing. Okay. All right, last question here. This is a tangent line problem. Okay, finding the tangent line, and this is also included on your study guide. Okay, so this is going to be, in general, y minus, I'll put it right here, y minus y1 equals m, or dy dx, x minus x1. dy dx is your m. That's your slope. That's not a very good m. There. Okay, so we already have our x and the y value, negative 1 and 1, so I can go ahead and start filling that in. Y minus 1 equals, we don't know what our slope is yet, but we do know x plus 1, x minus negative 1, which is x plus 1 here. And I just need to figure out my slope here. So the way I figure out my slope is I plug it into that guy right there. So I'll do dy dx with negative 1 comma 1 plugged in, which is equal to, so what this bar means is evaluate. Here, I can put brackets around it like this. Okay. Evaluate the slope at negative 1, 1. So this ends up being 1 over 3 times 1 squared is just still 1, minus negative 1. So 3 plus 1. So 1/4 is my slope here, 1/4. And there's your tangent line. All right. Now, as always, if you have questions, please shoot me an email. Please let me know. I hope this video helped, but if you need me to clarify anything, let me know.